Okay, so you've got a study guide. When in hindsight, there really isn't much that we've added from the first test to the second test. Primarily Eulerian and Hamiltonian graphs. So the Eulerian part is pretty simple. When is a graph Eulerian? Connected. All degrees are even. That would give me an Eulerian circuit. But what if I only needed an Eulerian? There you go. What if I only want everybody? Oh. But what if I only want an Eulerian trail? Two odds. Everything else is even. 2 odds. And what condition? Yeah, but what additional condition? Connected. Got to have connected. Don't forget, I mean, that's sort of pretty important. We talked a little bit about graph products, long cycles and long paths. I spent quite a bit of time going through proofs about Hamiltonian cycles and Hamiltonian paths. We had a degree sum condition that gives us a condition on whether a graph is Hamiltonian or traceable. That's not it's unlike Euler's condition. That is not an if and only if. So if the degree sum for every pair of non-adjacent vertices is high enough, then the graph is Hamiltonian or the graph is traceable. Traceable means, but let's start with Hamiltonian means what does?
Path or circuit.
Okay, which one?
Circuit.
Okay, so careful. Circuit allows you to repeat vertices. But this is right. What doesn't? What structure, a substructure of a graph do we have where we don't? Spanning tree. That's a tree. Circuit is again. We've talked about Eulerian circuits where we're allowed to repeat vertices. Hamiltonian means that there is a cycle. What's the difference between a cycle and a circuit? I've essentially told you just in the last 2 minutes. No repeated vertices or edges. Obviously, if you're going to repeat an edge, you would have to repeat vertices. So a cycle means that you have no repeated edges. Every vertex appears exactly once in the sequence on the cycle. Versus Eulerian circuit, where it not only does appear more than once, but in some cases must appear more than once. Okay, so that's a big difference between Eulerian and Hamiltonian. Eulerian, it's very simple. I'm going to leave this out. Okay. It's very simple. For Eulerian, there's a nice degree condition that determines exactly when the graph is Eulerian, when it contains an Eulerian circuit, when it contains an Eulerian trail. Okay? Don't forget connected. Okay, so long cycles. Then we talked about connectivity. So one of the things that's going to be important as we move on in the next 2 or 3 chapters is this idea of being connected. Okay, so the concept of connectivity is pretty clear. If I have a graph, then I can find my way from one vertex to any other vertex. Okay, then the graph is connected. But the 2 concepts that we've studied is, okay, so how do I destroy connectivity? So I can destroy connectivity. There's several ways I can destroy connectivity, but the ones that we've studied are removing vertices and removing edges. So a graph is K connected if the removal of fewer than k vertices, fewer than any k vertices, removal of fewer than k vertices, any fewer set, leaves the graph connected. Then the graph is k connected. It doesn't say that the connectivity is k. Connectivity k is now the measure. So what is the smallest, the order of the smallest set of vertices that I have to remove to disconnect the graph? Okay, so there is a difference between saying that a graph is k connected and the graph has connectivity k. Okay, one more time, k connected means that if I close my eyes, I choose any set of fewer than k vertices, then the graph, and I remove them, the graph remains connected. Now, it doesn't mean that if I remove there is a set of k vertices that I remove that disconnects the graph. Okay, that's the idea of having connectivity k. So to say that a graph has connectivity k means that the graph is, of course, k connected, but there is a set. There is a set of k vertices whose removal disconnects the graph. Any fewer does not disconnect the graph. So that's connectivity k, means that's the smallest number of vertices that disconnects the graph. Okay, edge connectivity, now we're going to remove edges to disconnect the graph. Okay, and again, a graph is k-edge connected, just like k connected. The removal of any fewer than k vertices does not disconnect the graph. K-edge connected means the removal of any fewer than k edges does not disconnect the graph. But having edge connectivity equal to k means that there is a set of k edges whose removal disconnects the graph. Okay, is that clear? Again, that's it. The words sound very similar, but in fact they're a pretty important distinction between being k connected and having connectivity k, being k edge connected and having edge connectivity k. Okay, the words sound almost the same, but there is an important difference between the two. One defines a parameter, another one tells you a little bit about the structure of the graph. Okay, and then we talked a little bit about connectivity for particular graphs, and then if you went to the second page, there's everything from the first test that is fair game. So just to remind you, we did a little bit about, several people have asked me about the C4, either any graph on 6 vertices contains either a C4 or its complement contains a C4. Okay, this idea of Ramsey theory. So that's something that, again, gives you practice at structure of graphs and how to deal with the structure of a graph and its complement and how they relate to each other. And that's important as we move forward. Okay, lots of definitions that I'm going to expect that you know these definitions, what a tree is, how many, if I have a tree of order n, a tree of order n. Oh, what is a tree? What's the definition of a tree?
No cycle.
No cycle. More.
Connected?
Connected. What if I drop connected? What do I have? No? Multiple trees. What's that called? Let's see. Let's just imagine I'm outside and I see, oh, there's multiple trees. What would we call that?
Forest.
A forest. Okay, so graph theory is just like real life in some way. Okay, so a forest is a graph that has no cycles, and a tree is a connected graph that has no cycles. And what's the number? How many edges are there? If I have a tree of order n meaning the number of vertices is n, then it has n minus 1 edges. Okay, and if you forget that, let me offer you the advice of, gee, why don't I just draw a tree on 5 vertices? If you drew a tree, doesn't matter which tree you drew on 5 vertices, how many edges would it have? 4 edges. Okay, and you would if you tried to put in more, it would either have a cycle, and if you tried to put in less, it wouldn't be connected. Let's be temperamental today. Okay. Habel Hakimi, I'm not sure. That's that's something. We talked about degree sequences. There's a degree sequences turns out to be important, but not something that is easy to deal with. I don't imagine that there would be another Habel Hakimi problem on the exam, but certainly understanding a lot of the concepts from the first 5 chapters, I think is important. There will be a little bit heavily on paths and cycles, Hamiltonian, as well as connectivity. Okay, so that's basically the test. It is not made up yet, but soon. I'm working on it. Okay. Questions?
I know you already said this, but just to double check, the edge connected, vertex connected is to leave the graph disconnected. And then,
Okay, so there's to say that a graph is k-connected. K-connected means the removal of fewer than k vertices leaves the graph connected. Listen to those words. The removal of fewer than k vertices leaves the graph connected. Okay, so obviously it has to start connected.
right.
Okay, and the removal of any fewer than k leaves the graph connected. Now it doesn't mean, so what would it mean to say that G is k connected? G has connectivity k. So let me actually write something on the board. So what does,
That would mean it's k connected and it's not k plus 1.
yeah, okay. So it's k connected but it's not k plus 1 connected. So that means that there is a set. Okay, not being k plus 1 connected. If it was k plus 1 connected, every set of fewer than k plus 1 vertices would leave the graph connected. If it's not k plus 1 connected, that means that there must be a set smaller than k plus 1 that disconnects the graph. And if it's k connected, then that set must be
K.
k.
And then with edge connected, it's okay if it's disconnected. We're just talking about, we're leaving it with the same number of components.
Same number of
Okay.
components, right.
And same thing with edge connectivity.
Edge
Same
connectivity, right.
number of components.
Exactly.
Okay,
Yep.
thanks.
Okay?
So that means the connectivity is K or is K connected?
So this means, so let's make it clear. This means that it's k connected.
Okay.
The removal of fewer, to say that
Fewer than
the
K.
connectivity of G is k, means the removal of fewer than k vertices leaves the graph connected. Okay? But having connectivity k means that there is a set of k vertices that disconnects the graph. Okay?
Yes.
So what you wrote on the board, that equation means,
Means,
doesn't mean vertex.
so one more time. So to say that connectivity of G is k means that there's no set, so that if I take any set less than k, the graph remains connected. G remains connected. But that there is a set of k vertices that disconnects the graph.
So that means all of it. What you wrote on the board means all of that.
What I wrote on the board means all of that.
Okay.
Right. So to say that connectivity of G is equal to k, I mean, the words, it's like the same words. Wait, the connectivity of k, the connectivity of G, and G being k connected. I mean, they're kind of the same words in different order, but they have pretty different meanings. Connectivity is a parameter that actually evaluates the smallest number that disconnects the graph. Okay, so if this is the smallest number that disconnects the graph, then if I take any k minus 1 vertices, then the graph remains connected. Remove any fewer than that, the graph remains connected. Okay. So yes, this says a lot. This is a
So
pretty
that
strong.
means K of G is equal to 4.
So if K of G is equal to 4, so if the connectivity of G is equal to 4, that means that the removal of 3 or fewer vertices, the removal of fewer than 4 vertices leaves a graph connected. So in particular, it means that G is connected. Okay, so G is connected. But it does also say, but this adds the extra condition that there is a set of 4 vertices that disconnects the graph. Okay.
Maybe clarifying in that if you're 4 connected, then you're also 3 connected, and you're 2 connected, and you're 1 connected.
Right.
Right.
So one more time, I'll write down, so to be K connected, I know these are, it's a tricky word. This is the actual measure, this is the connectivity. To say that it's K connected means that the removal of fewer than K vertices leaves a connected graph. So what Dalton is saying is, notice, if I have a K-connected graph, then I also have a K-1 connected graph. Let's make sure we understand that. So the removal of fewer than K vertices leaves a connected graph. To say that it's also K-1 connected means the removal of fewer than K-1 vertices leaves a connected graph. So if G is K connected, G is K-1 connected. Is that clear? Did the words make sense? Okay, they almost sound the same, but they're different. Okay, which is different than the connectivity equaling K. Okay, so of course if it's K-1 connected, then it's K-2 connected, and so forth. Okay, each one being sort of weaker than the other. So it's a sort of a tower of connectivities. It's a tower of connectivities until I get to the biggest one. Okay, so the idea of being K-connected, there's a relationship between K-connected and what the connectivity is. You just have to find the largest K for which G is K-connected. Okay, if G is K-connected but not K+1 connected, then in fact we must know that the connectivity is equal to K. Okay. Okay, so then we talked to, again, the connectivity, edge connectivity, same idea. Now instead of removing vertices, I'm removing edges, okay? And disconnecting the graph, we're removing edges and not the end vertices. Okay, so for example, if I look at, let's imagine that this is a K5, and here's another K5. So now I'm just removing, let's look at this graph. So the connectivity, just for the heck. Okay, so this is a graph, just so we all understand, this is a graph on 10 vertices. So it's got 2 K5s, and then these 4 edges between them. So how many edges do I have to remove to disconnect this graph? 4 edges? Okay, so I would have to remove all of those edges. By the way, I also could remove these 4 edges as well. Okay, exactly this is adjacent to 4 vertices here. So this vertex, if I remove these 4 edges, then this would isolate this vertex. So the edge connectivity, we would have connectivity 4. No set of less than 4 edges disconnects this graph. Okay, if you remove 3 edges in here, or if I remove 3 edges, it looks, gee, if I just remove these 2, we're close, but I'm still connected with this vertex here. What's the vertex connectivity? You changed your mind, okay. All right, what 2? Okay, so if I remove these two vertices, that disconnects the graph, or if I remove these two vertices, that disconnects the graph. Notice if I remove just one of this one and this one, that's no good. If I remove this one and this one, it's still connected. So I'd have to remove at least three if I did that. So it's much better if I just remove these two. Okay? Questions? Okay, the difference, again, there's a fine difference between the parameter edge connectivity and vertex connectivity and being K-connected or K-edge connected. Again, K-edge connected meaning the removal of fewer than K edges leaves a connected graph. Okay, and a lot of the test will sort of depend on the definitions from the first test. I expect you to know components of the Peterson graph. We know the Peterson graph. Let's see, distance, trees, degree sequences. I probably won't give you a Havel-Hakimi. Some results, I put some results down here. They should be, there aren't that many that came from the first couple chapters. Long cycle. Yeah, so, okay, so,
Comprehensive.
okay, so, okay, so, the word long is so this is, here's n minus 2, and here is 2.
特别像牛奶，
And let's,
特别像牛奶。
so this is k2 n minus 2. Okay? I understand it's contrary to what our understanding of the word long is, but what is a long cycle in this graph?
That doesn't mean the longest.
It doesn't necessarily mean the longest cycle, okay? But in fact, in this graph, what is the length of the longest cycle? The 2. Everybody knows what this graph looks like, right? All those points, those are all independent, and these two are independent. What's the length of the longest cycle?
4.
4. That's it. And in fact, it's also the length of the shortest cycle. I know it's the length of the shortest cycle because if there was a shorter cycle, it would have length what? 3, but this is a bipartite graph. What do we know about all of the cycles in a bipartite graph? Even. So all cycles in a bipartite graph are even, and hopefully that makes sense because I've got to go back and forth between the two parts, always picking up an even number of points. Okay, so there's no 3 cycle in this graph, and of course we don't, 2 cycles would require multiple edges, and we're not, at this point, we're not dealing with that. Okay, so a long cycle doesn't necessarily mean that I have the longest cycle. So if I want, so if I have a cycle of length n minus 2, if I have n vertices, I might ask for a condition that gives me a cycle of length at least n minus 2. That would be a long cycle, okay? So maybe that was a bad use of terms, but often we're looking for the longest cycle, but sometimes we just want long cycles. Okay, and as we start to get to some of the application problems, we may only care about getting a long cycle, a cycle that has at least half the vertices. That might be, and the word long will depend on what the problem that we're looking at. Other questions? Again, there'll be, I probably went through this, there'll be some definitions, there'll be some, it'll be very similar to the first exam. It'll be similar but different. Okay, let's just say it like that. So I'll bet there's going to be something to prove, and there'll be some at least some questions that require you to understand the definitions that we've gone through since the first test and before the first test. Okay? Okay, but it won't include matchings, independent sets, matchings, and couples. Okay, which is where I want to go back to right now. Okay? So, you're all pretty quiet. Okay, so we've talked about a matching. We've talked about independent sets of vertices. Let's independent set of vertices. What's an independent set of vertices? So it's a set of vertices where they're pairwise non-adjacent to each other. Okay, so independent, so they're pairwise non-adjacent. So that's an independent set of vertices. Now, some books and some applications will talk about independent sets of edges, but that gets a little confusing, maybe. So rather than looking at independent sets of edges, this book calls it a matching. So what would be a matching? Okay, so they're edges that are pairwise, what? Pairwise, when we have two edges, they're pairwise non-incident. Okay, so in other words, they don't share a vertex. So if I have two edges, that would be a matching. They don't share any vertices. Okay, they're edges that don't share any vertices. Okay, so where we left off on Thursday. So I want to turn to page 265. So we'll come back. We'll be coming back to looking at independent sets of vertices soon. But one of the things that's stressed is this idea of matchings in graphs, matchings in particular bipartite graphs. So I want to look at on page 265. So remark 7.2.5. So let G is a bipartite graph. With bipartition X and Y. So bipartition means that the two independent sets are called X and Y. And in many of the applications and many of the problems that we're going to look at, applications is really the key here. We have a bipartition. We have a natural bipartition based on the particular application. So I'm going to go back to potential medical school students and medical schools. Okay, so if X are the medical school students, and these are the medical schools. And the reason I mention this is because they really use applications of bipartite graph to placing as many medical school students as possible. So medical school students have the schools that they want to go to. Okay, so maybe they all want to go to Harvard. And maybe no one, only some people want to go to Colorado. Here's Harvard, here's University of Colorado. Okay, so everybody wants to go here. Everybody, this is on everybody's list, but this is only on like a few people's list. Okay, and what medical schools, doctors are still in pretty high demand, and they want to be sure that that they get as many students as possible trained as doctors. So there is a clearinghouse. There is the medical society, and I don't know what the society is, but they actually look at the students and the students rank the schools that they want to go to, and then so the students rank the schools, and then the medical schools rank the students. And they try, and there's a nice program that optimizes the pairing off of students to schools. Okay, and trying to please everybody and be sure that the schools get enough students and that the students get something close to their first choice. If they only put one school down, it's most likely they will not get a choice. Okay, so it's made clear that they need to be a little bit broader in their choices for medical school. And I'm not sure. At some point, the law schools wanted to do a similar sort of thing, but I don't believe that ever happened. Now, the thing is, there's not a one-to-one match. So it's not a match. It's not a matching as we know it. So the schools actually take a set of students. So here are the students that would go to Harvard, and here are maybe the students that would go to Colorado. Okay, and there is some overlap in this matching, but they try and, again, using some sort of optimization, they try and optimize the school's choice and the student's choice. Okay. So what's most important for a bipartite graph? So let's look at a bipartite graph. So here's my bipartite graph. There are no edges between the blue, and there's no edges between the red. Then if I'm going to, let's call this X and this Y, I want to completely match off X to Y. I want to be able to match X off to Y. So what's the first thing you can, and let's just imagine, just to give you a clear picture, imagine that these are the medical schools and these are the medical school students. There are some students that don't get into a medical school. So I want every one of these to be matched to a vertex in Y. What can you tell me about the size of X and the size of Y?
Y would have to be at least as big as that.
Yes, so the order of Y is greater than or equal to the order of X. Okay, so I'm looking at remark 7.25. To be able to complete, so G contains, and G is a bipartite graph, contains a complete matching from X to Y. From X to Y, then the order of X must be less than or equal to the order of Y. If I'm going to have a complete matching, and they don't have to be vertical. I just drew like that. Let's just so you know that. Okay, there's nothing vertical about this. Okay, we're just matching these guys to these guys. Okay, an obvious case is if I'm going to match off everything in X, then Y has to be at least as large as X. This should be common sense. Okay? If G contains a perfect matching, so what does a perfect matching mean? What do you think a perfect matching means?
One by one.
It's just perfect.
One by one.
What do you mean by that?
One student corresponding with one school.
Okay, one student to one school, and one school to one student.
Yeah.
So a perfect matching in bipartite graph with parts x and y means that edges contain all vertices of x and y. It's just perfect. Okay, now I'm just talking about a matching. This gives me more than a matching. So let's put the hospital example, the medical school example out for a second. I'm just looking at a graph and I want to find a perfect matching, which perfectly, the word perfect is there for a reason, perfectly matches all the elements in x to all the elements in y. So if this is going to be the case, then as it says here, if there's a perfect matching, then the order of x must equal to the order of y. That's just obvious.
Well, so if the perfect matching means the edges contain all the vertices x and y, common x just have edges with more than one y. So that's also the edges contain all the vertices.
So say that again.
So one x just connect with more than one y.
Yeah, so certainly this is just a subgraph. Let's go back. This is just a subgraph of the graph.
Oh,
Okay, it's a subgraph. Okay, but the converse is not true. Okay, so here's what I want you. What do I mean the converse is not true? Okay, that means if x is equal to y, can you find a bipartite graph that doesn't contain a perfect matching? Okay, so let's be very simple about this. Let's suppose x has 4 vertices, that's x, and y has 4 vertices. Can you give me a bipartite graph that doesn't, so the x and the y's are equal, but it doesn't have a perfect matching? Yes.
How about that one?
This one? This is perfect matching.
No, yeah. X and Y are equal, there's no perfect matching?
Yeah. Yeah, that's cheating. Put some edges in it.
All right, 1.
Put a lot of edges in it.
Oh, okay.
Okay, all right, okay. So yes, even though x and y are equal, but in fact, let me point out that if this is the whole graph, then I could reimagine x and y and make x and y not equal. What do I mean by that? I mean, let's make this, let's make them just, here's a new x, those 4 edges, and then these 3 additional points. Okay, they're not adjacent, so that's okay. And then this guy. Okay, so I could rearrange it so that the sets, the parts are not the same size. Okay, then that's not saying that's enough, but yes, you're right. That certainly is an example. Can you give me one with edges? So one with edges, the parts are the same size, and let's put a lot of edges in there.
Connect every element of x to the first element of y.
Okay, now we're talking.
Every element of y to the first element of x.
Like that?
So every element of y to the first.
Yes, sorry, yes. Let's try that again. I'm starting over. I can get my x's and y's confused. So every element of y is adjacent to the first element of x, and every element of x is adjacent to the last element of y.
That works.
Yeah. It looks like a lot of edges. We can't match everything, we can't match everybody off? No, in fact, I mean, it's pretty clear that, if I look at these three people, there's only one choice for their match. And vice versa, if I look at these three jobs, or whatever I'm applying, there's only one person that can be matched to those. So there's no perfect matching. What's the largest matching that I get in this graph? What is the largest matching? And when I say matching, the largest matching, what's the largest set of independent edges? Or how big is the largest set of independent edges? I can just keep asking that the same way. Yes. Can you find one? Sure. I can find one. There's one independent edge. Can I find a second independent edge? I can find the second independent edge. Can I find a third? Fourth? Okay, if I can't find a third, I can't find a fourth. Okay. So again, the important thing is that we're going to want to have as big a matching as possible. So again, G contains a complete matching from X to Y, then Y has to be at least as large as X. There is a perfect matching, so a perfect matching where everybody in X gets matched to everything in Y, and everything in Y gets matched to everything in X. Then that only happens if the two sets are equal. And if G contains a complete matching from X to Y, then M is perfect only when X is equal to Y. So those three conditions sort of at least set the stage for when we have a perfect matching, which is, there's a reason they call it perfect, right? Okay, so, okay, we got 35 minutes. So we've talked a little bit about applications, and by the way, let me point out, we're only looking at matchings at this point in bipartite graphs, but there's no reason that I can't, let me put your favorite graph up, my favorite graph. Okay, so there's no reason why I have to only look at bipartite graphs. By the way, is this bipartite?
Try.
It's tripartite. How do you know that it's not bipartite? What do we know about cycle lengths in a bipartite graph?
They're even.
All cycles are of even length. Bipartite graph has all cycles of even length. Can this be bipartite? Because
Cycle 5.
you have 5 cycles. You have many 5 cycles. In fact, you probably have 7 cycles. Maybe 9 cycles. Okay. So that's pretty far away from bipartite. But it does have a matching. It does have a perfect matching, I think. Does it have a perfect matching? There's one obvious perfect matching. Well, maybe it's not so obvious. Say that again? I saw the hands move. Do I? These?
Yeah.
Yeah, that's a nice, perfect matching. Notice all 10 vertices are matched with distinct edges. Okay, so even though this is pretty far away from bipartite, it does have a perfect matching. So we will get to finding matchings in graphs in general. Right now, the most important thing that we're looking at this moment is these assignment problems and finding matchings in bipartite graphs. Okay, it's not, but I want you to know, it's not the only things that we care about. Okay, we're gonna care about matchings in graphs in general in a section or two. Okay, so what I want you to look at is, so problems 1 through, 1's pretty simple, 2, 3. Okay, so let's start with 4 through, I want you to get to 13. So let's do 4 through 13. So I want you to take 15 minutes, 4 through 13. You might want to start with 13 first, because that's not a bipartite graph. At least I don't think it's bipartite. Let's quickly look at the graph on problem number 13. Is that bipartite? Because it has C5s. It also has C3s. Okay, what's wrong with the C5 and the C3? Okay, so a bipartite graph can't have any odd cycles. You start here, go down here. You can't go anywhere here. The only place to go is back up. So the only cycles are even cycles in a bipartite graph. Okay, so once again, from number 4 to number 13. Did I say 4 to 13 or 5 to 13? 4. Okay, go. Let's hear some chatter. I got those microphones. They're just out there waiting for chatter. No, I only have 4 microphones. You want to join the table? You want to join another table? Okay. What the heck?
Chatter.
Okay, so who doesn't have a perfect match?
Does not have a perfect match. But it does have a match with 7
It
edges.
does have such a match.
So, would you join this group? They have a microphone. I didn't hear much talking amongst yourselves. I don't actually know the microphones.
Yeah, no. I would always tell her to, I'm not on Facebook right Alright, what's number 13? Yeah, so this is 9. How do you go about a
Right,
proof
right.
of not having a perfect matching?
Yeah, okay, all right, let me, yeah. We'll be coming back to
Yeah, I'm sure.
connectivity, yeah.
We'll see
Yeah.
it again and again. Oh, I will.
So just the cross one? Just the cross one.
Is this what you do for the rest of your life?
Connectivity, I don't know.
Each of these, so to have the perfect matching, this one has to match, and this one has to match. These four have to match, because so anyway, all 3 of these have to be these are.
And you could not, this edge and this edge could not be in the matching because you would be missing this vertex.
I think I got this actually.
Yeah, so it'd
So,
be like they did
proof by picture.
So,
So, all I've done is isolate
something would be left.
this section of the graph.
This,
So,
there's
let's
no way
see.
to do a matching for this.
Well, so these 4.
you're gonna end up losing out on one of, I'm sorry to be touching your screen, you're gonna end up losing out on one of these 4 vertices?
Okay, the goal of contradiction, assume there's a contradiction. So I would think these 4 have to all match with each other some way. Do you agree? Because if this guy
This
matches
is
in here,
gonna be on
then we've only got 3
Thursday.
Perfect.
Okay, I think you got
Okay,
that.
so if these 4 all have to be connected to each other, that means this guy has to be connected, this has to be in our matching. Okay, and that means all 3 of these have to be in our matching.
So this for virtues will be like have 2 edges matching, like a matching. So that so finally all these 3
Also, classic 2 color. You don't know cover one
Yeah,
another.
and this class is the last to play copy.
Yeah, those ones are really cute.
Oh, yeah.
That's true.
Yeah, I saw
This
this
grading scale.
brilliant.com or something like that, and it just has like
Sure.
You know, I got an 88, and you just write in the box. It might be,
But they made me.
I wonder if you'd say, yeah.
Weird things.
Graph theory stuff.
Yeah, yeah. And it was like,
Is it a section that they have, or is it just like?
I think there's, I don't know if it's actually, there seems to be several.
It's not a complaint of mine, because I can't get an A plus because
And then there's all
I've
kinds.
gotten
They
one.
just
No,
they
no,
have like a 10 by 4. And you're supposed to color 2 by 2.
my history
Or no,
class would
sorry,
have been A plus
4
last
by 4.
semester. Okay, so now, want to go to,
It was basically the exact same.
I'm sorry, Dr. Jacobson, after we finish number 13, do you recommend that we work backwards, like, I'm just asking, do you recommend that we go like 12, 11, 10, 9, or?
Yeah, have you done 13?
Yeah, or should we go back to 1 before?
Yeah,
Watch your
doesn't matter. I mean, they're all, none of them are
Okay,
difficult.
so that would be, yeah, whatever,
Practice that,
whatever
practice
the
idea of matching
Can you-
and independence.
It's got a
Well,
multiple.
we'll see if we agree with that claim that now
Okay.
it's difficult.
Ben, it's also to give you an idea of the applications.
Oh, yeah.
If you look at number 5, I think, there's an interesting application of coding
Oh,
and bipartite.
yeah, well, I've never really been much of a purist. I like to apply everything.
There you go. Did I say the right one? Is that 5 is a coding problem?
Yeah, code words.
Code words, yes.
And you say that any 4 by 1. So yeah, that's specific. Think about something. Yeah, so I think on a 10 by 10, you're gonna have 4 squares.
So these are all vertices right here, A, B, C, I'm assuming.
Because whatever in the corner is gonna be, you got an odd number of 2 by 2s.
That's a prefix subgraph, isn't it? I mean, they're not sort of vertices.
Is that number
they
12?
are vertices,
Or
or
you-
they
on
can-
or something?
Sorry, I was
Oh, no,
talking
I see.
different,
Okay,
it-
all right,
Yeah,
okay.
really similar as well.
Okay.
I saw one on the internet that was, instead of 2 by 1 dominoes, it was 4 by 1 domino, and on a 10 by 10. And you couldn't do it. And luckily, I had seen the answer, so it was a very easy to get the answer for 12.
Okay, everybody, 13? Let's see if 13 is, we got 13? Okay, so prove the following 3 regular. This is called the triple fly swap. I don't make these up. You just go along with it. Does not have a perfect matching, but does have a matching with 7 edges. Okay, so there are 16 vertices. So a perfect matching would have how many edges? 8 edges, if it was a perfect matching. Okay, so who's going to prove to me that this doesn't have a perfect matching? Come on, someone.
So, well, because the largest pairing we can find is 7. And it has 16 vertices in total, so.
Wait, 7, you have 7 edges that has 16 vertices?
Yeah, we have 7 independent edges, and we have 16 vertices,
Right.
so.
Okay, but is that a proof that there's no 8 independent edges?
Well, kind of,
You tried them all.
yeah.
By exhaustion.
So there are 3 parts of this graph, and for each part there are at most 2 independent.
Okay, all right, so there's a proof. Okay, so let's talk about this graph. I won't draw the rest of it. If there's a perfect matching, that middle point must be matched with something. Which one do you want to match it with? Bottom? Bottom. Okay, so if there was a perfect matching, then this would be, we would use one of these edges. That means that this can't be used, and this can't be used. Is that clear?
Yes.
Okay, if there was a perfect, but what's left here? That would leave, yeah. That would leave this graph. That would leave these 2 graphs on how many vertices? Okay, one more time. If this edge is used, this edge can't be used, and this edge can't be used. So that would mean that I have this subgraph on 5 vertices, and I would need to match everything off. But what's the greatest number of vertices that I can match off on these 5 vertices? 4.
4.
And the same goes here. So I would be able to find 2 edges here and 2 edges here, this edge and 2 edges. That gives me a matching of 7 and no matching with 8. Okay? Okay, once you, again, this idea of disconnecting the graph and, in this case, having odd pieces becomes pretty important. Okay, all right. Again, these shouldn't be hard, but they're hopefully interesting. So we've done 13. I'm going to work backwards. How about 12? Michael can't answer this. How about 12? Let's see. I got a 6x6 grid shown where I've cut the upper and lower square off. You're given, let's see, so at 6x6 it had 36 boxes. When I take one box off in the right-hand corner and left-hand corner, then I only have, let's see, 36. Now I have 34 boxes. And I'm giving you 17 dominoes. 17 dominoes. And a domino covers exactly 2 boxes. So I'm going to give you 17 dominoes, cover all the squares. How is this a graph theory problem? How are you going to construct a graph out of this? I mean, we're in graph theory, so this should have something to do with graphs.
Boxes are vertices and show you an edge in the boxes and show
Oh,
you
there we go. Okay, so I'm gonna try and draw the whole thing. So it's 6. It's how big is it? It's, so I have 5. So this is a middle row. So this is the row above it, and then I got another one of these, and then another one of these, and then another one of these, and then one of these. Okay, and this is so that's 6. This only has 5, 6. Okay, everybody sees, right, this is the pattern. Okay, there's 30 boxes. Sorry, there are 34 boxes. And I'm gonna give you dominoes. My dominoes are 1 by 2 dominoes. I give you 17 dominoes. 34 boxes, 17 dominoes, cover all the boxes. How does this relate? What has this got to do with a bipartite graph? We're in the bipartite graph question. Okay, let me give you an easier problem first. So now I have 36 boxes, and I give you 18 dominoes. Can you cover all the squares?
Yeah.
How do you know?
Put every domino horizontal.
Every domino, so here's a domino, here's domino, here's domino, 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 all the way down to this. Well, why can't I do that here?
You can't split the domino in half.
You can't,
Split your domino.
no, you can't cut dominoes. Dominoes always come together. But, okay, so why can't I go like this? I put a domino here, and a domino here, and a domino here, and a domino here, and so forth. Well, what's wrong with that?
One of the red.
Okay, one more time. The question is, what does this have to do with bipartite graphs?
Is set X 17?
Which
And set
17?
Y?
Let's see. What?
I'm trying to pair 17 dominoes with,
Well, we only have, in fact, I would only have, let's say I have, how many dominoes? I have 34, 17 dominoes, so I have 34 points. Everybody, let me give you the hint. Think checkerboards. Tell me about what a checkerboard is.
Alright, so if you start to say which partition each one's in, like bottom corner will be in line, so checkered board black.
What does a checkerboard look like? There.
Yeah, black, and then diagonal will be.
Okay, so wait a second, sorry, just wait a second, hold on, don't go anywhere. Okay, so checkerboards are black and white, red and black, I don't know,
Red.
red, black, red, black, red, black, red. So if this is red, and this box here is black, red, black, red, black, red, black, red, black, red, black, red, and so forth. Let's fill them all in. Black, red, black, red, black, red, black, red, black, red, red, black, red. This is a black, and this is red, black, red, black, red. What does this have to do with graphs? You sort of told me.
So 36 one was even red and blacks, but then you removed 2 blacks.
Oh.
There's,
What? Okay, so the bipartite graph is going to have 34 vertices. 34 vertices. They're all going to be, what have I removed? When I say removed, that means what isn't here?
2 black squares.
2 blacks, so I have 34, so how many blacks do I have? In the whole checkerboard, how many reds, how many blacks? It's 36 boxes, 18 and 18. I'm removing 2 blacks. So there's 18 reds and 16 blacks. Take this away. And if I was going to cover all of the squares with dominoes, that would correspond to a matching of how big? There are 34 squares. How big would the matching be? 17. But what's the biggest matching we can have in this graph? 16. Is that clear? It's a very clever proof of. One more time. We have this checkerboard where I've cut out opposite corners. So rather than having 18 reds and blacks, I now have 16 blacks and 18 reds. So my bipartite graph has 16 blacks and 18 reds, and there's no way to match them all up. The biggest matching that I can have is how many dominoes? What's the biggest matching I can have? 16. So I could have 16, but that would leave 2 red boxes empty. Okay, is that clear? So that's a quote-unquote nice application of bipartite graphs. Okay, keep going. Okay, so starting back at number 4, 4 is pretty simple. 5, I mean, basically these are examples of how to build a bipartite graph from a bunch of words. And I don't mean code words, right? So let me look at 5 for a second. I have 5 code words: AB, ABC, CD, BCD, and DE. I want to transmit these code words as messages, but I don't want to send the whole code word. What I would like to do is have an abbreviation for each one, and the abbreviation be distinct. So, tell me what the code words are again. AB,
ABC,
ABC,
CD,
CD,
BCD,
BCD,
DE.
DE?
Yeah.
Okay, and I would like to only represent these with A, B, C, D, E. So I would like a matching where A represents only one of these. So if I can find a matching, so I'm going to look at a bipartite graph where each of the singletons are adjacent to, let's see, B is adjacent to this one, C is adjacent here and here and here, D is adjacent to here and here and here, and E is adjacent only to this one. So if I find a matching, and I think the matching is pretty simple, right? Let's see. A represents this word, B represents this word, C represents this word, D represents this word, and E represents this word. So if I write my code as anytime I want to send the word AB, I simply send A. And as long as the receiver understands my matching, and there may be multiple matchings, as long as the receiver understands the matching, when the receiver receives A, they know you're transmitting the word AB. When it receives the letter B, it knows that you're sending the word ABC. Okay, based on this matching. Okay? So there's another application of matchings in this case, bipartite graphs. Okay? How about number 6? Anybody got number 6? 7 teachers for each of, hopefully there are 7 subjects. Chemistry, English, French, geography, history, math, and physics. Math and physics are separate. So there are 7 different subjects, 7 different teachers, and here are the qualifications. So we're going to apply bipartite graphs to assigning teachers to classes. And it's based on what the teachers are qualified to teach. So A is qualified to teach math and physics. B is qualified to teach chemistry, English, math. D, R, S, T, and W. So we get a bipartite graph. Notice none of the teachers are connected to each other. That makes sense. None of the subjects are connected to each other. So I've got a bipartite graph on 14 vertices, and I'm looking for a matching with 7 edges.
These 2 teachers right here, let's do either math or physics. These 2 teachers are Mr. Tan and Mr. Allen. One is doing math, the other is to do physics.
Well, this person has math too, so maybe this is math.
Well, every teacher only gets one subject, right?
Yeah.
So Miss Adela and Mr. Tan, one of them would have to do math, the other would have to do physics.
Physics are only two, one of them, next is only physics, right?
No, what's the same?
Oh, they both have math.
Yeah, it's their only two. Yeah.
Yeah.
One of them, Miss Adela and Mr. Tan, one has to do math, the other has to do physics. That means Mr. Singh has to do chemistry. Which means Ms. Bowie has to do English. We have history, French, and geography left. This person has to do geography. These person, one does history, one does it's possible. So what part B determine the maximum number of qualified teachers? 7. It's the max annual one. They can't get away with 6. And there's no need for 8. So the max annual is about 7. If they want to fill all the vacancies. Yeah. It's just easy. I mean, all you have to do is recognize Miss Adela, Mr. Tan, and Mr. Stamps, and the problem solved itself.
So the way I did the first two, is I looked at how many degrees there is, and she got yeah, so like this one, we have degree 1, 2, yeah, and then just the lowest degree, work my way up. So usually one has to go with 7. Yeah, this one here was, 4, within 1, because it only had degree 1. So I just started with 10, degree 1, so then worked my way up. So this was to, it was male, we used to turn it down, which was already taken, or the reaction.
These may be exact date, you agree? Did you get married in a church, or was it like a draft or a wedding?
I just started
Because so did How long does it take to get married?
All right, so do you have the teachers assigned? Are we covering all the classes? Okay, again, it's a bipartite graph where the teachers are in one part, the classes are in the other part, and we have 7 teachers and 7 classes, and we'd like a perfect matching. Okay, it makes sense that in this case, we have a nice application of perfect matchings to bipartite graphs, and maybe there'll be conditions that will tell us when there is or there isn't. So the last thing I want to talk about is how many perfect matchings in, let's start with CN. So what is CN? Cycle? So, and the N means what?
Number of vertices.
CN is, so CN is a cycle on N vertices. Think small. How many perfect matchings are there in C4? 2. How many perfect matchings are there in C5?
No, 0.
0. Why 0?
No perfect matching.
Because there's what?
No perfect matching.
There's no perfect matching. Okay, perfect matching means that you're matching everything up and you've got 5 vertices. That would be hard to match everybody up. Okay, so if N is odd, the answer is none. If N is even, 2. Okay, so C4, there's 2. C6, there's exactly 2. C8, exactly 2. Okay, let me jump to KPQ. Perfect matching. What can you tell me? If there's going to be a perfect matching, what can you tell me about P and Q?
Equal.
P is,
Equal.
P and Q are equal. Okay, if P and Q are not equal, then there's no way that I can match everybody up. So let's assume that P and Q are equal. Now, how many matchings are there? So take the first vertex, and how many ways can I, let's imagine that I have a, so P and Q are equal. So let's take a KPP. KPP. So X1, X2, XP, Y1, Y2, YP. How many ways are there to pair X1 up? How many ways? What? But how many, what is that? What, no, so I can pair X1 up with
YP. P of them.
P of them.
Okay.
P of them. This is Y1, this is Y2, this is YP. So I can pair X1 up with P different guys. Once I pair X1 up with someone, what's left? What graph is left? Pull this out. What graph is left? P minus 1, P minus 1. So how many ways can I pair X2 up? P minus 1. I pull that edge out. How many ways can I pair X2 up? Sorry, X3 up? P minus 2. P minus 3. Down to, finally, I'll only have one edge left. So that's P factor. And finally, Kn. First of all, n better be, what can you tell me about n?
Even.
Even. So let's look at how many perfect matchings are there in K4? 3. K6?
3.
Okay, we'll start with that. So I want to know how many, so first of all, n must be even. How many matchings, how many perfect matchings in K2n are there? By the way, if I ask you for the number of perfect matchings in K2n plus 1, number of perfect matchings in K2n plus 1? It's like a trick question. 0. Okay, see you Thursday.
So, you take the edge out.